Okay, so a minute ago we talked about how you can test the hydraulic conductivity of relatively small samples, like the size of a jar of peanut butter or something. But what if you want to have a hydraulic conductivity test over a broader area? One question you might ask yourself is why? Why would you want to do that? Well, a lot of states require that you conduct what's called a percolation test or a Perc test for short. Before you put in a septic system. So if you don't know, people that live in town have sanitary sewers, right? So when you flush the toilet or when you use the sink, the water goes down into, goes underground into these pipes, right, and is funneled to the wastewater treatment plant. We'll talk about how the wastewater treatment plants work soon. But the water goes there and it's cleaned and then it's released back to the environment. But if you live out in the country, then you don't have that option, or if you live out in some sort of semi-rural area. And so you got your house here, and when you flush the toilet and use the sink and that sort of thing, the water is piped not into a broader wastewater treatment system, but it generally goes underground to some buried tank here, which is called a septic system. Septic tank. And septic tanks, every once in a while, trucks can come out, these big trucks, and they put in a hose and they suck everything out. But the septic systems are designed to actually operate without having to do that. The way they work is, if we zoom in on this septic system, so here's the land surface here, and here's the septic tank, right? That's what this is. And the septic system has a bunch of sort of walls or baffles in it, so that the water can't just flow. It comes in here from the house, and then it gets released over on this side. And the idea is that the water just can't come in and run out. It's got to kind of migrate its way around. This is the side view. The top view, that's visible. Top view might look something more like this, where you have these walls sticking up from the ground that don't go all the way up. So the water comes in over here and goes out over here, and so the idea is it's got to migrate its way around. It takes a long time to get through, and as it's moving through, basically what's happening is it's being biodigested. So there are bacteria and different microorganisms that are added to the tank, that live in the tank, that break down the organic matter. And so the idea is that by the time the water has moved its way very, very slowly over the span of days or weeks or months from one side of the septic system to the other, by the time it's released, it's been broken down sufficiently that a lot of the solids have been removed, and it's been dramatically cleaned up. But you still wouldn't want to drink the water that's coming out of the other side. So these things are buried, right? This is buried underneath the ground. Oh, that was the top view. Hold on. So what you want to do is you want to dilute that water. There's an old saying that some of you may have heard, which is that the secret, no, excuse me, not the secret, the solution to pollution is dilution. The solution to pollution is dilution, right? So when you have this this water that's coming out of the back of the septic system, right? What you want to do is, you don't want to drink that. You have the water table, say, down here somewhere. So the idea is that the effluent, the water that's coming out, which is the not particularly great water, as it migrates its way down through the sediment to the water table, it's being further worked on by organisms in the sediment, and it's being fanned out a little bit, and it gets to the water table, and now say the water is going is this direction. So you begin to get this kind of diluted plume of this stuff, and if your well for your house is way down here, by the time the water makes its way all the way down here, if that's far enough, it's been sufficiently diluted, it's been sufficiently cleaned by the septic system and by the organisms in the soil and the ground that it's essentially safe to drink. That's the idea. Now, of course, there have been plenty of cases where people have houses too close to each other's wells and they get sick from the contaminated water. But if you do this properly, it's a pretty very low density area. It's fine. Okay, so what's the point of this? Going back to hydraulic conductivity. Well, if you release the water out of the septic tank and the hydraulic conductivity of this sediment isn't high enough, then what happens? Then this contaminated water doesn't go anywhere. It just builds up. It's not capable of moving fast enough out of the way because the hydraulic conductivity of the sediment is too low. So before you can put in a septic system, you have to make sure that the ground around the septic system has a sufficiently high hydraulic conductivity. And that's where you do, or that's why you do a Perc test. You want to get a bulk sense, a generic sense for the hydraulic conductivity of your yard, say. And if the hydraulic conductivity is high enough, then they grant a permit that allows you the builder to come in and dig a pit and install a septic system. If it's not high enough, then you have to take some sort of remediation step to increase the hydraulic conductivity, which is more than we're going to talk about. Okay, so what do? Well, you hire a company and they come out and they will come to your house. Here's a tree, here's a house, and you want to put the septic system, say, over here somewhere. So what they'll do is they'll come in and they'll auger a hole, and I'm going to make this much bigger in just a second. I just want to show you from a more distant view what they're going to do. They're going to auger a hole, and they're going to fill the hole with water, let's say, and let's say the water table is down here. They fill the hole with water, and they watch how fast the water inside the hole drains out. Okay, so the water height in the well is going to drop with time, right? And its ability to leave the well and to flow into the ground is a function of that ground's hydraulic conductivity. Make sense? So by measuring how fast the water level in the well drops, you can calculate hydraulic conductivity. That's where we're going with this. All right, so let's look quickly at what this well looks like. So I'm going to kind of zoom in down here. So what it would look like is you'd auger the hole. Okay. And you are going to insert into it a piece of PVC pipe. It's going to go down here. I didn't do that very well. Keep it down the middle. Okay, that's just PVC pipe. And it has a certain radius, which we'll call little r. That's the radius of the pipe. And the pipe is solid pipe until you get to the very bottom. And then it's got these tiny, tiny little, and I would unfortunately show you this if we were in class, and I can't show you from a distance very easily, but just these tiny, tiny little saw cuts into the bottom of the pipe. And those are called slots. Each one of those little slices, very, very thin slices into the bottom here. Okay? They're called slots. And this interval is called the screen. That's the well screen. Okay? And when you put that down in there, you've got space between the dirt over here and the well. And what we generally do is we pour in gravel. Really well sorted, clean gravel. You just buy it in bags and you pour it down in there. You fill it up. And you fill it up about that high. So this is gravel. And the reason you put the gravel in there is the gravel has a very, very high hydraulic conductivity, so it's not going to interfere with our measurements. The water can flow through there fine. But what it does stop, it stops the sides of the well from collapsing. Right? You don't want the the ground here to kind of start caving in. It wouldn't work. And it also keeps little bits of dirt from clogging up the screen. Okay, so this is called the well screen. The rest of this, everything from here up, is called the well casing. Right? It's just the solid pipe. And then sometimes what they do is they backfill this here with cement, or usually you don't use cement because then it's it's hard. You use what's called bentonite. Bentonite you buy is these little tablets, and what they are, they're little basically clays. And when you add water to it, they soak up the clay soaks up the water and becomes this very kind of impermeable layer. So what you're doing basically is you're sealing off the top. You're sealing off the well screen from the from higher up. Okay, that's the idea. All right, so the only way that water can get out of the well is if we were to pour water down into this tube, right, which we're going to do in a minute, is to flow out of these little slots. The bottom is plugged. Let me just make that sure. The bottom of the well is closed. So the only way the water can get out is through these little slots. Okay, that's the idea. So on this diagram, we're going to define a couple of distances here. The height of the gravel, we're going to call L, just for length, right? Because water can flow into the side there and go down pretty easily. And the distance, well, you know what? Let me draw this again because it's getting a little crowded. Let's draw this one more time. Okay, so the height of the gravel is L. The radius of the inside of the pipe is little r. The height of, the distance from the inside of the pipe to the outside of the gravel there is called big R. Okay, and the equation that we use is pretty straightforward. You just have to do the test. Let me give you the equation first. The equation for calculating hydraulic conductivity is K equals little r squared times the natural log of big L over big R divided by 2L times T naught. So everything here should be pretty straightforward except for one term. K is hydraulic conductivity. That's what we're solving for. R squared, so this is little r. This is the radius of the pipe itself. Natural log of L, big L divided by big R, L here. And then there's this T naught function. So you then wonder, what exactly is this T naught thing? Well, T naught is what you have to calculate, right, in order to determine what the hydraulic conductivity is. Everything else here is just pretty much straight. So let me show you how we calculate hydraulic conductivity. So let's say that what we do is we're gonna put a let me do this again. This whatever. The oh, I should have told you this before. Perc tests are also known as slug tests. Perc test, slug test, same thing. Okay. So here's what you do. Let's say that we take a well, right, and we are going to I don't know. Let's say that in this case, let's say that the water table is right here. Here's the screen. Okay. So we drill this thing, we install it, we walk away for a day, we come back, and now water has flowed into the well through the screens such that it's sitting at this height, right? This is the water table, so this is where the water would be inside the well. Make sense? The groundwater doesn't care that there's a well or there's not. That's just the height it's going to rise to. All right. So what you do is, a couple different ways to do this, but what's often done is you take a big piece of metal called a slug, right? And it's on a string, and you drop it down inside this well. So when it drops down in, it sinks to the bottom, sits here, it's a solid piece of metal. And what happens is, obviously for a split second, or for a couple of seconds, the height of the water in the well, because you drop this slug in there, the water shoots up to about here, right? Just inside the well. But over time, the water wants to go back to its original level, so the water begins flowing out through these slots until it's back to its original height. Make sense? So I'll just draw this now. So it originally was like that. So I'll do it in a couple of steps, maybe. So originally, you had the water here, right? Then we draw, that's sort of stage one. And stage two is we drop a slug down into the bottom, slug of metal, and the water rises up inside the well a little bit higher than it otherwise would be, right? Because the water displaced it upward. We wait a few minutes, and that water, right? The water with the slug down there. Oops. That water is going to be flowing out of the screen back until it comes back to its original height. You still have the slug down here. Okay, and this thing's on a string. Okay, now when you get to that point, you're ready to start the experiment. So you ever understand what happened? You got a well here with water in it. You drop a slug of water, or excuse me, a slug of metal to the bottom. The water rises up inside the well. You wait a few minutes for the water to drain back out until it's back to its original height. Now you have this slug of metal sitting at the bottom of the well. All right, so what you do after that is you pull the slug out, right? And what happens is for that split second, or for just a few seconds, the water level in the well is lower than the water level on either side, right? And so what happens here are the slots. So what happens is the water rushes in from the surrounding ground and wants to raise the level of the water back inside the well. And what's going to determine how fast that water rushes back in? Well, what's going to determine essentially is the hydraulic conductivity of the surrounding sediment. And that's what we're trying to measure, right? We're trying to measure this K. So let me just give you a little example of how this would work, and then you can get a sense for what this mysterious T naught variable is all about. So let's say we do a slug test. A slug test is performed by lowering a metal slug into a well. These wells, by the way, they're given a special name. They're called piezometers. A piezometer is a monitoring well, meaning it doesn't have a pump connected to it. If you just drill a hole in the ground and stick a pipe down there, that's a piezometer or monitoring well. A slug is performed by lowering a metal slug. Slug test is performed by lowering a metal slug into a well, a piezometer, that is screened in, or that is formed in coarse sand. the inside diameter of both the well screen and the well casing is 2 inches. 2 inches. The screen is 10 feet in length. And we record water level every second after the slug is removed from the piezometer. Okay. And what we get is something that looks like this. So basically what you're going to do is you're going to have a column that you're going to fill out that's going to say time in seconds. And you're going to say, what would this be? Depth to the water, say in feet. And you're going to have a change in water level, which is abbreviated as H. And then we're going to have this final value over here, which is H over H naught. Okay. So you have time over here in seconds, so like 1, 2, 3, 4, 5, 6, 7, 8. And what's going to happen, right, is at time, say, time 0 before you start, say it's at like 13.99 feet to the water line. Well, as soon as you pull the slug out, the water in the well drops. So the distance to the water rises, right? You have to go further down to get to the water. So 14.87, 14.59, 14.37, 14.20, 14.11, and so forth. And basically what you're seeing is the distance from the land surface to the water is decreasing, and it's going to keep decreasing 14.11, 14.05, 14.03, and then until finally it gets back to 13.99, which is where it was initially. So the water level dropped and then rose back up as water flooded back into the piezometer until it gets back to the same height as the water table, and then it's not going to change anymore. So what we want to do is we want to calculate the change in the water level from its ambient value. So what we're going to do is we're going to subtract this 13.99 from each one of these different values. So 13.99 minus, excuse me, 14.187 minus 13.99. So this minus this would be 0.88. And that is the H naught value that you see over here. H naught. In other words, it's the time, it's the maximum change in water level is a way to think about it. Okay. And then the change in water level is going to decrease as the water level rises back up. So it's going to be 0.6, 0.38, 0.21, 0.12, 0.06, and so forth until you get all the way back to 0.00. 13.99 minus 13.99 is 0. That's where this comes from. And then you just do the math. You divide H, which is each one of these, divided by H naught. And so 0.88 divided by 0.88 would be 1.00. 0.6 divided by 0.88 would be 0.682. 0.38 divided by 0.88 would be 0.432, 0.239, 0.136, 0.068, all the way down until you essentially get to zeros again. Okay, So it's a lot of numbers, but the idea is really simple, right? You drop a slug in, you wait for the water to go back to its original level, you pull the slug out, and what happens is the water level goes down quickly and then slowly sort of climbs back up to where it was before. You calculate the change in the water level per second, and then you divide the change in the water level by the maximum amount of change in the water level, this H naught, and you get these numbers over here. Okay, so when you've done that, you just need to plot it. Now remember, we're doing all this because we're trying to find the hydraulic conductivity of this thing, this land, and we're going to use this equation. And we know everything in this equation except for T naught. That's what we need to solve for, and that's what we're doing with this math. Okay, so what you do is you have a graph where on the y-axis it's h over h naught, and on the x-axis it's time in seconds. So this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, so forth. And that's just a normal scale. And on this axis, it's one of these semi-log plots. So you have 0.01 here, 0.1, 1.0. Every time you go from one big tick to the next, it goes up by 10. So this would be 0.02, 0.04, 0.06, 0.08. And I'll give you these this graph that you don't have to worry about it. And then this would be 0.2, 0.4, 0.6, 0.8, so forth. And you just plot the numbers that we calculated here on this graph. And what you end up with is, something that's going to look kind of like that. And once you plotted them, I'll give you an example of this to do, don't worry, so you get some sense of how it works. You just draw a best fit straight line, or have Excel do it for you. Right, there's a best fit straight line through the data. And then you go to wherever T naught is equal to wherever h over h naught is 0.37. So you go over here to wherever it's 0.37, which would be right there, and you go down, and that time, whatever that time is there, is T naught, and that's the number. It's not 0.37. You use T, or h over h naught, right? Whatever h over h naught equals 0.37, that's what you use to then find T naught. And that T naught goes in here, and out comes the hydraulic conductivity. So we'll just wrap this up by finishing this exercise. So if T naught in this case was 1.8 seconds, let's say. If T naught was 1.8 seconds, then to solve for K, remember it's R squared natural log of L over R squared natural log of L for R 2L T naught. So we would have 0.083 feet squared. I've converted everything to feet. The natural log of 10 over 0.083 divided by 2 times 10 times 1.8 seconds, which is T naught. And out comes 79.2 feet per day, which is K, which is the hydraulic conductivity of this backyard. So if 79.2 feet per day is high enough, then you're allowed to install the septic system, and if it's not, then you've got to do some more work. Sorry that was so long, but that's just the nature of this kind of exercise. It takes a while to get through it.